Welcome back for another scientific literacy lesson. This is the finale of a three-part series about quantum computers. In part one, I covered the basics of traditional digital computers. In part two, I talked about the distinction between digital computers and quantum computers. And in part three is going to be about the phenomenal power of quantum computers. I'm also going to reference the earlier videos quite a bit, so if you haven't seen those, go ahead and check those out. Quantum computers would store and manipulate data in qubits or quantum bits. A digital computer with an n number of bits can store information in any combination of 2 to the n. Quantum computers do the same thing, but they can also take advantage of superposition. So they can hold information in 2 to the n number of combinations, but for 2 superpositions for each of those combinations. And they can hold those combinations simultaneously. Put another way, if you have 2 classical bits, they can be arranged in any number of 4 possible combinations, 0, 0, 0, 1, 1, 0, and 1, 1. But if you have 2 qubits, they also have 4 possible combinations based on their orientation, and then 2 possible superposition probabilities attached to each of those, which means there are 8 possible combinations for 2 qubits. And they hold those all simultaneously until they are measured. This means that if the possible number of combinations for a traditional computer is 2 to the n, where n represents the number of bits, the total number of possible combinations for a quantum computer are 2 to the 2 to the n, where n is the number of qubits. Now, if a working quantum computer existed with just 300 qubits, as compared to the billions of capacitor bits in your smartphone, that's enough qubits to store as much information in binary as there are atoms in the universe. And it would also have the computing power of all of the existing computers on the planet combined. Some of the challenges with quantum computers, first of all, they wouldn't actually be a replacement for standard digital computers in most cases. For example, the qubits aren't literally occupying every possible combination all simultaneously. Also, in the process of measuring them, we also lose some of that superposition information. When that information is output, it is only output in binary, so ones and zeros. The primary advantage would be in the speed of certain types of calculations based on those superpositions. One of the types of calculations that would proceed much faster would be the traveling salesman problem. In this problem, a computer is asked to find the most efficient route of travel for a salesman that is traveling to a number of cities in the United States. As the number of cities they must visit increases, the difficulty of the problem increases. Modern digital computers can handle this task pretty easily when there's a small number, just a handful of cities the salesman must visit. Traditional computers are very good at handling simple problems like this with a small number of variables. What they do is they look at every possible route between the cities that the salesman intends to visit, calculates the distance of every possible route that connects all of those cities, and then compares those distances in series to figure out which one is the shortest route. But every time a new destination city is added to the problem, the number of possible routes doesn't increase linearly, it increases exponentially. For example, if you have 14 cities, there are roughly 100 billion possible routes that connect all of those cities on the map, which means a computer is going to run a calculation for every one of those routes and compare them to see which one is the shortest. And our modern digital computers can do that task in about 100 seconds. That's not too shabby. It becomes problematic when we add up to 22 intended cities. For a computer to handle that, they have to compare 10 to the 19. That's about 10 billion, 100 billions of possible routes. It would take the average digital modern computer about 1,600 years to compare all of those routes and find the most efficient route. At 28 cities, it would take a modern computer roughly the same amount of time that the universe has existed so far to calculate all the possible routes and determine the most efficient route between those 28 cities. A quantum computer, on the other hand, since it has the capacity to compare those routes simultaneously instead of in series, doesn't have to wait for the last route to be calculated before it can start calculating the distance on the next route. Which means if a quantum computer was asked to find the most efficient route between 28 separate cities, in theory, they would be able to complete a calculation like that in a few minutes instead of 14 billion years. Another challenge is we're talking about using components of individual atoms as the storage units for qubits. It's incredibly difficult to manipulate and to image individual atoms or atom components, and on top of that, they're highly susceptible to disruption and interference called decoherence, which is when information is lost from the quantum phenomenon. When decoherence occurs, the resulting errors are referred to as bit flips and phase flips, which is when the spin direction, which correlates to the 0 or 1 in binary, unintentionally flips, or when we lose superposition information. So where do we stand with quantum computers now? Well, last week, IBM unveiled two critical advances in practical quantum computing. The first is the ability to detect and measure the two types of quantum errors, that's the bit flip and the phase flip, simultaneously. The second is a qubit design structure that is the first to have been demonstrated to actually be able to successfully scale up to larger dimensions. Previously, we could only identify and correct either one or the other type of decoherence, so that's the bit flip or the phase flip. We couldn't handle both at the same time. Also, most arrays of qubits that we were studying and working with were arranged into linear arrays, which we knew were not practical to scale up into larger multi-qubit systems. The researchers changed the typical arrangement of qubits from a linear array to a square type chip. And that allowed for both the simultaneous identification of the two types of quantum errors and the scaling. We're still quite a ways away from having functional quantum computers available for civilian use, but we're routinely seeing some progress from researchers at places like IBM and elsewhere around the world. As of today, billions of dollars in research funding is being applied to the quantum computing research and development teams at IBM and other corporations and organizations all around the world, because it's identified that quantum computing may become a very real possibility within this decade, and the possibilities are exciting.